Hi students, today we are discussing about composition of functions. In order to understand the composition of function, I have taken three sets A, B, C. Now if we take a function f and in which it is moving from A to B, and then beginning with the same set B, I take another function g from B to C. Okay. By take a random element x here, after applying the function f, it become f of x. Okay. Now beginning with f of x, after applying the function g, we get our final product g of f of x. Okay. In short, the new function which moves from A to C is defined by A to C, which is defined by g of f of x, or simply g of f. Okay. Mathematically, if a function a from b and g is a function from b to c be two functions, then the composition of f and g denoted by g of f and is defined as g of f is a function from a to c given by g of f of x equal to g of f of x for all x is an element of A. You know, it is like considering a series of machines in a factory. So once a raw material x is put into the first machine, it exited to the next level and create f of x. Now taking this as the input of the next machine under the mapping G, it creates the final element G of f of x. It all like a chain reaction. There are two very important points to remember. The first point is, if a function f from A to B, f is a function from A to B and g is a function from B to C, we know that first consider our first function f. This is our domain and this is the range of function f. And let us consider the g function. This is our domain and this become our range. So the first point is to be noted that the range of function f should be subset of domain of g for g of f to exist. Similarly, the range of g, that means range of g should be a subset of domain of f for f of g to exist. Okay, I repeat. First note is, if a function f from A to B and g from B to C, the range of first function f should be subset of domain of g for g of f exist. Next one is, range of g should be domain of f for f of g exist. In general, it brings us to a conclusion that f of g not equal to g of f. Okay, f of g and g of f, they are not the same. Okay. Note that for f of g, g is operated first. G is operated first followed by f. In case of g of f is operated first followed by g. So looking at the very first question, we have given a function f from R to R and f of x equal to x square, and another function g from R to R and g of x equal to 2x plus 1. We need to find f of g and g of f. So let's start the solution. So beginning with the f of g, we know that f of g equal to f of g of x. Right. In place of g of x, we have g of x equal to 2x plus 1. That is, f of g of x become f of 2x plus 1. Okay. If f of x equal to x square, then f of 2x plus 1 become 2x plus 1 all square. So here is our answer, f of g equal to 2x plus 1 all square. Similarly, talking of g of f, we know that g of f is g of f of x, right? And in place of f of x, we have x square, so this become g of x square. If g of x equal to 2x plus 1, then g of x square become 2x square plus 1. So here is our answer, g of f equal to 2x square plus 1. I hope you understood. This is our second question. Here f and g are defined in terms of ordered pairs, and we need to find out f of g and g of f. Before we do that, we need to at least have this f and g sorted. In the previous class, we know the domain of the function is the first coordinate. I hope you remember. So here, the domain of a function f, domain of function f is a set containing 1, 3, 4. 1, 3, 4. And range of function f are the second coordinate. So that is the range of f is equal to the sets containing the elements 2, 5, 1. 2, 5, 1. Okay. Similarly, the domain of function g will be 2, 5, 1. 2, 5, 1. And the range of g will be 3, 1. Okay. So, if we write the function f in function form, we get f of 1 equal to 2, f of 1 equal to 2, f of 3 equal to 5, f of 3 equal to 5, and the last one is f of 4 equal to 1. F of 4 equal to 1. Similarly, for g function, g of 2 equal to 3, g of 5 equal to 1 and g of 1 equal to 3. G of 1 equal to 3. Clear? In order to begin with the f of g, we start with the whatever elements are there in domain of g. So we need to find f of g of 2, f of g of 5, and last one is f of g of 1. Domain of g is 2, 5, 1. That is, we need to find f of g of 2, f of g of 5 and f of g of 1. Okay. So starting with the f of g of 2, we know that f of g of 2 equal to f of g of 2, and here we can see that the value of g of 2 is 3. So we substitute here, we get f of 3, which further gives us f of 3 equal to 5. Okay. Next, f of g of 5, and it can be write as f of g of 5, and here the value of g of 5 is 1. So f of 1, the value of f of 1 equal to 2. The last one is f of g of 1, which is equal to f of g of 1. The value of g of 1 is 3. That means f of 3, the value of f of 3, g of 1 equal to 3 and value of f of 3 equal to 5. Okay. So finally we get f of g is a set containing with 2, I have 5, 2, 5, ordered pair 2, 5, 5, with 5 I have 2, that is ordered pair 5, 2, and with 1 I have 5, the last ordered pair is 1, 5. So this is the answer of f of g. Okay. Likewise, beginning with the GOF, we take GOF, we take the elements from the domain of f. So we need to find g of f of 1, g of f of 1, g of f of next 3, and g of next one is g of f of 4, g of f of 4. The domain of function f contain 1, 3, 5. So we need to calculate g of f of 1, g of f of 3, g of f of 4. Here we know that g of f of 1 is g of f of 1. The value of f of 1 is 2. So substituting here we get g of 2, and we know that g of 2 equal to 3. Next one is g of f of 3, which is equal to g of f of 3. The value of f of 3 equal to 5. So substituting here we get g of 5, and g of 5 will be 1. And the last one, g of f of 4, is equal to g of f of 4. We know the value of f of 4 equal to 1. So substituting here g of 1 here, and the value of g of 1 is 3. Okay. So finally we get our g of f is a set containing ordered pairs. With the 1 I have 3, so 1 3, and 3 I have 1 3 1, and the last one with 4 I have 3 4 3. So this is the answer of G of f. I hope you understood. This is our next question. In this question, function from R to R and is defined by f of x equal to x square minus 3x plus 2 are given, and we need to find out f of f. So let's start our solution. In this question, here we have only one function. The function from R to R, and we have find the composition of function with itself, that is f of f. That means f of x equal to f of x, and we know the value of f of x here, so substituting we get f of x square minus 3x plus 2. Okay, so just to understand, let's name it as y. So which will be equal to f of y. So our f of y will give us y square minus 3y plus 2. Now putting back the value of y, for this we get x square minus, we know the value of y is x square minus 3x plus 2. So this y square become x square minus 3x plus 2 whole square minus 3 into y become 3 into x square minus 3x plus 2 plus 2. Okay, simplifying all these, f of x become x raised to 4 minus 6x cube plus 10x square minus 3x. Okay, so this is our answer. Does the composition of two functions satisfy commutative? Let's see an example. Let a function f from R to R and g the function from R to R defined by f of x equal to 2x and g of x equal to 3x square. So let's find composite of function f and g first, and then g and f. So first, composite function f and g, that means g of f. You know that g of f equal to g of f of x. Okay, substituting the value of f of x here, we know that f of x equal to 2x, so we get g of 2x here. Okay, and if g of x equal to 3x square, then g of 2x become 3 into 2x all square, which is equal to 12x square. Okay, Now let's find the composition of g and f. That means f of g. We know that f of g equal to f of g of x. And substituting the value of g of x, here the value of g of x is 3x square. So f of 3x square, we get f of 3x square. And if f of x equal to 3x, then f of 3x square become 2 into 3x square. Hence, the value of f of g of x equal to 3x square. Observing the values of g of f and f of g, the values of g of f not equal to value of f of g. Hence, we can say that two functions g of f and f of f are unequal. In general, the composition of function does not satisfy the commutative property. So, I hope you understood. Let us now prove some important theorems related to composition of function. The first theorem states that if a function f from a to b and a function g from b to c are 1, 1, then g of f from a to c is also 1, 1. Let's recall when its function is said to be 1, 1. A function f from a to b is defined to be 1, 1 if the images of distinct elements of a under the function f are distinct. That is, for every x1, x2 is an element of a, f of x1 equal to f of x2, which implies x1 equal to x2. With the help of this result, let's begin the proof. And we are given that a function f from a to b and a function g from b to c are 1, 1. Which implies that for every x1, x2 is an element of a, we have f of x1 equal to f of x2, which implies that x1 equal to x2. Let's name it as equation number 1. Also, for a function g of x1 is equal to g of x2, because function f is we have given function g is also 1, 1. So, g of x1 equal to g of x2, which implies x1 equal to x2. Let's name it as equation number 2. To prove that g of f, our g of f is 1, 1, we need to show that if g of f of x1 equal to g of f of x2, then x1 equal to x2. So, we have g of f of x1 which is equal to g of f of x2. Okay, and we know that the g of f of x1 will be g of f of x1 and g of f of x2 will be g of f of x2. Okay, from equation number 1, f of x1 equal to f of x2. Okay, so which implies that f of x1 equal to f of x2, which also implies that x1 equal to x2. So this will become g of x1, and the second term will be g of x2. Okay, here we are replacing this f of x1 by x1 and this f of x2 by x2. So this will become g of x1 equal to g of x2. From equation number 2, this implies that from equation number 2 we get x1 equal to x2. So we have started from here and ended the fact that x1 equal to x2. Therefore, g of f is 1 function. Our second theorem states that if f is a function from a to b and g is a function from b to c are onto, then function g of f from a to c is also onto. So let's start our proof section. Let us consider an arbitrary element z, which is an element of set C. Since G is onto, that exists a pre-image of Z under the function G such that G of y equal to Z. G of y equal to Z. Also, we have given that f is onto and henceforth y is an element of set B. There exists an element x is a subset of A such that f of x equal to y. So first let us name it as equation number 1, and here let us name it as equation number 2. Okay. Therefore, g of f equal to, we know that g of f equal to g of f of x, right? We know that f of x equal to y from equation number 2. So we replacing f of x by y, and also we know that g of y is set from equation number 1, which is equal to z. Okay, here it is from equation number 2 and this from equation number 1. Thus, corresponding to any element Z is an element of set C, there exists an element x is an element of A such that g of f equal to z. Hence, g of f is onto. Please note that in general, if g of f is 1, then f is 1. Similarly, if g of f is onto, then g is onto. This is our third theorem, which states that if a function f from x to y and g is a function from y to z and h is a function from z to s are the functions, then h of g of f equal to h of g of f, or it satisfies the associative property. So let's start our proof. Consider any arbitrary elements. X is an element of set X. So let's start with the LHS. Our LHS is equal to h of g of f. We know that it can be also written as h of g of f. Okay. Further, which is equal to h of g of f of x for all x in capital X. Now let's move to RHS, right? Our RHS is equal to h of g of f, and it can be also written as h of g of f of x. Further, h of g of f of x for all x in X. Observe that LHS and RHS are equal. Hence, h of g of f equal to h of g of f. Hence, the composition of function satisfies associative law. Hence, the composition of function satisfies associative property. Okay, I hope you understood.